Welcome mechanics of materials students. In this lecture we're going to expand the concepts that we've established about yield criteria, especially with Tresca, to looking at what happens when we have to be concerned with fracture. So in our discussions about yield criteria, we established that materials yield based on applied shear stress. So it was really important that we understand either what the max shear was if we're going to apply Tresca, or kind of its strain energy analog, the deviatoric strain energy that was going into things changing shape. There are times when we have to be concerned not with yield but with fracture, and that's when we have materials that, are going to break before they bend. So if we look at a stress strain curve for two materials that are pulled in uniaxial tension, material B is the kind of thing that we were examining with our yield criteria. And what we were really looking for was at how we were going to avoid going beyond this point sigma yield that would be this point if we were in uniaxial tension. And we were kind of applying, okay, where do we find that same point in a more complex stress state? Well, there's some materials that aren't going to yield. They're going to break. They're going to come. They're not going to exhibit any kind of yield behavior. But we do know the stress that's associated with fracture if we pull it in uniaxial tension. So the point is we have that data, and in fact we might test this in a different direction. We might look at going into compression, say, and we might establish a compressive fracture stress, which is probably going to be a lot further down. So generally speaking, the uniaxial compressive stress that corresponds to fracture of a brittle material is much higher than the same one that would be necessary to result in fracture if we were in tension. Okay, why is that? Let's take a little, we're going to take a little deviation into material science and kind of think about how things fail. So all materials have a certain distribution of pre-existing flaws. Think of them as little microscopic cracks. And when those cracks are loaded, they can propagate. And the criteria for a crack propagating is literally defined in terms of strain energy. So if we load a material up by applying stress, it's going to have some strain, and we can use our expressions for strain energy, both total or deviatoric, to characterize the strain energy in that material due to its stress state. The material might like to go to a lower energy state, so what it might do is swap that strain energy for surface energy of a new surface. And if it takes less energy to create a new surface by advancing the crack, then it gets released from the strain energy that it now doesn't have to carry, then there's a net energy decrease to advance the crack even without applying more load. So we stretch a material, we're applying a particular stress to it, we have a certain amount of strain energy, and we've got some starting flaws. If some of those are lined up such that their strain energy at their tips is more than the energy to create a new surface by advancing the crack, they're going to propagate, we'll get catastrophic failure. We learned in our von Mises yield criteria derivation that we could maybe do some yielding at the crack tip, and then we would introduce a whole new bucket load of energy in terms of yielding that material, and we captured that with our J2. So generally speaking, this leads us to two rules of thumb for design. Don't use brittle materials. A brittle material isn't going to have deformation mechanisms available to blunt a crack. Crack's just going to go. It's going to trade new surface area in the form of advancing that crack straight for the strain energy from loading. It doesn't have any other way to dissipate that energy. That's very dangerous. In the unavoidable times when you have to use brittle materials, you want to keep them in compression. So our typical example of this is concrete. So we can use concrete very safely, provided we don't ask it to carry any tensile load at all. We make a composite, and we use steel reinforcement or other types of materials that are strong in tension. We let those carry all the tensile load, and we only rely on the concrete to carry compressive loads. So in this section, what we're going to do is basically do the same thing we did with yield, except we're going to say, okay, maybe we have to use a brittle material. And we know from uniaxial tests, so stress in one direction, not a complex load, we know what tensile stress and what compressive stress corresponds to failure. So we're going to create a failure envelope not out of equivalent shear, but actually tensile compressive normal stresses, our principal stresses. And we're going to construct a failure envelope and say, okay, if we have to use a brittle material, keep it in this envelope. So consequences are a little more important. So we're going to start with our friend, the Mohr Circle. And so these two circles represent the results of tensile test, in the case of the little circle, and compression testing on a brittle material and to failure. So we're yanking on the material. We haven't applied any shear stress, so our applied stresses are our principal stresses. So this small circle represents our material in tension, and so this particular tensile stress corresponds to when it would have broken. Okay, so here's the corresponding shear, which is less important because we're not going to enable any deformation mechanisms, regrettably. And here's the much higher in magnitude compressive stress that also corresponded to failure. So these 2 points are empirical data. Somebody went into the lab, took a tensile test specimen, stretched it, squished it in one direction, and came up with those 2 numbers. And because we knew it was uniaxial, we were able to construct a Mohr circle. And what we know is that if we create a failure envelope or an envelope, shear versus tensile, by drawing lines tangent to these 2 circles, that envelope will contain the different combinations of compression and tension that would not lead to failure. So we can take those tangent lines and basically summarize them by plotting normal stresses against each other. So we're thinking now, we're expanding what we did in uniaxial in the lab to maybe a biaxial stress state out in the field, because things are rarely loaded just in uniaxial tension. So we're going to suppose we have a plane stress, which is a little bit more common, state out in the field, and we're looking at the different combinations of applied stress in the X and Y where you're not going to get failure. So we'll basically plot a Tresca envelope where we'll plot the ultimate tensile strength in both directions. So if we're only applying stress in one direction, so which would correspond to this point or that point, we're going to fail at sigma ultimate tensile, which is this point here, because we're effectively just back in that uniaxial state. And likewise with compression, either here or here. And then we've got our diagonal lines, which represent a combination of loading states. And of course, if we have combinations of loading that are in the same direction, it's going to be the higher load that's going to define what you have to limit. Okay, so anything in this shaded irregular hexagon is, I've kind of squiggled here, will be not failing. Anything outside it would represent failure. So other point, if you're comparing this to the shape of the yield stress Tresca triangle, the biggest thing to remember about this one is it's kind of much fatter in the compressive end, corresponding to the significantly higher stress to failure in the compressive direction for just about any material, but definitely brittle materials. Okay. So we can think of a scenario where we have a true multi-axis loading. We got gray cast iron. We know from a uniaxial tensile test in the lab It has a uniaxial tensile ultimate strength of 170 megapascals and compressive uniaxial strength of negative 680. So big difference. So there's our brittle material acting differently. And we're going to take it out in the field, and it's going to see 100 megapascals of tensile stress in our x direction, 300 megapascals of compressive stress in the y, and we're going to twist it a bit. We're going to give it a shear stress of 100 megapascals. So this time our applied stresses are not the principal stresses. So we got some shear. So we're going to ask, does it fail? So the first thing we need to do is figure out what are those principal stresses for actual stress state. So we're going to do a little mini Mohr circle here, and we're going to say, okay, we've got stresses in two orthogonal directions, sigma xx and sigma yy. Those are separated by 90 degrees in the part, which means they're separated by 180 degrees on the Mohr circle, which means they'll define the center point. So we have negative 300 and 100 we can plot on our x-axis. This is just going back to our stress transformations. So we know that our center is at negative 100, and we can use our actual measured shear stress of 100 megapascals to define our y-axis. And so now we can use 100, 200 as our two legs, and that gives us r of our right triangle. So our radius is 200 of our Mohr circle is 224 megapascals. So if we take negative 100 and we subtract 224, that gives us our max compressive stress. So that's our principal compressive stress, negative 324. And our max tensile is 124. So now we can't compare either one of those alone to what the material will withstand because we're applying them at the same time. So we have to go back to our envelope here, where these two values of sigma 1, sigma 2 would be corresponding to tensile. So each one of those is 170. So this point here is 170, 170, and this point is negative 680, negative 680. So this came from our test data. So we can just literally plot these 2 points in this shape. And with that shape, then all we have to do is plot sigma 1, as we'll go over 125 and we'll go down 325. So we'll plot a corresponding sigma 1, sigma 2, where sigma 1 means first principal stress, most tensile stress. So that's 124. And our most compressive stress is negative 324. So we're going to plot sigma 1 comma sigma 2 as a coordinate point. And we're going to find that it falls outside of our envelope. So that means the thing failed. Our combination of tension, shear, and compression that we applied was outside of the envelope that's defined to be non-failing, and that envelope was defined by uniaxial compressive and tensile stresses, but we used our stress transformations and the concept of our Tresca failure envelope, which were those tangents to our Mohr circle up here. We used just this construction that came out of a test to basically say we can take a complex loading that includes 3 different components and then relate that back to 2 data points from uniaxial tension and predict failure. This is not perfect, but it certainly allows us to leverage the data in our handbooks to great advantage. And it's also a really, really good warning to us that when we step outside of single axis applied stresses, we can't go apply those values back to handbook values. So for instance, if we just had 124 megapascals sigma 1 and sigma 2 was like 0, then we'd be here and we'd be good to go. It's interesting that the combination of the shear and the compression drove us outside of our allowable envelope. So This is a fabulous application of our Mohr circle, our Mohr stress circle, and a really simple concept of our Tresca yield or failure envelope to predict failure for something that is a much more realistic stress state. So that is it for this. Main points: don't use brittle materials if you don't have to. If you do have to use them, keep them in compression. Do not directly compare uniaxial ultimate values to your applied values unless they're also uniaxial. If you have a multi-axis stress state, which might include shear plus any other normal axis, use the failure envelope to compare the entire stress state to your failure envelope from your test data. And that is it for this lecture.